All right, good morning, everyone. My penmanship is just trash this morning. All right. Looks like another beautiful day today. It's kind of nice, helps a little bit. Get some sunshine. And then it's going to be like 40. It's like this ridiculous cold front coming in here too. All right, so let's get started today. We have a lot to work on. Let me see, make sure I am recording. Okay, double check. We're going to talk about 5.3 and 5.4 homework questions today because we have a quiz on that after class. And then after that, we'll take, hopefully have some time to do some additional examples. 5.4 is kind of, we'll do like maybe one or two. I'm more interested in 5.5. That's a really important section, so I want to do lots of examples if we can from that. I do have some time after class. If you have some additional questions that you wanted to answer, I'll hang out after class for a little bit today. Quiz 11 will be posted right after class. And then next week, we're going to have an extra Monday class because we have a short week next week. So we'll have an extra Monday class. We'll do some more 5.5 questions. Tuesday, we'll do some review. And then the final exam will be posted after class on Tuesday. Okay, and then, yeah, it'll be due by the end of the day on Wednesday. That is the plan. Any questions about the plan, timeline, grading, anything like that? All right. Well, let's get started then. Oh, I should have had the homework up. Let me open up the homework here. Let's do them in order so I don't have to click back and forth here. We'll start with 5.3. That was the fundamental theorem of calculus, right? So who wants to get us started with some questions from 5.3?
Can you go over the setup for 15?
Yeah, let me open
Yeah, that's 5.4. Never mind.
Okay, all right. So we'll hold on to that one. I'm going to type it in the chat so I don't forget. 5.4, 15. Okay. So anyone have any 5.3 questions? Fundamental theorem of calculus?
Can you go over 65 for 5.3?
Let's open that one up here. Loading, loading, loading. This is what I mean. Like, I don't want to click back and forth. Page of your book, you just flip back and forth, but here, like, everything takes a while to load. All these symbols. 65, you said?
Yes.
All right. Let's grab that one. All right. So this is all about what does a definite integral mean when you have some context for the function. So I guess part of this is there's some language here. What does this marginal revenue mean? The marginal revenue function. There might be some examples in the section explaining what that is. Marginal revenue, which is this R prime of X, it's a rate of change. It's the rate of change of the revenue. And so it's kind of like how much additional revenue you get from selling the next thing. So it's revenue, ours is hundreds of dollars per unit. So it's how much additional revenue you get from selling the next unit. It's a rate of change, but it's not over time, it's per unit. So if you get like, so here R prime of X is equal to the cube root of X. So what this means is R prime of, get an easy one here, 1,000 would be cube root of 1,000, which would be 10. So what that means is approximately when you sell the 1,001st item, so the, oops, not dollars, the next item gains or gives you well, let's see, it's in hundreds of dollars, so it actually gives you 1,000 additional revenue, $1,000 additional revenue. Units are kind of weird here because it's $100 per unit. So it's a rate of change, and it's marginal means you have 1,000 items and you have whatever your revenue is. Well, the marginal revenue means how much additional are you going to get for that 1,001st item. Okay, that's what marginal revenue is. So now we're asked here, interpret the integral of the marginal revenue in the context of the problem. And then it doesn't give us an A or B yet. That's in part B. So part A says, what would the integral from A to B of R prime of X dx? So again, the key is R prime is a rate of change of revenue. So a definite integral gets you a net total change. Net change in revenue. And the A to B here is not from time A to time B, they're units. So it's the net change in revenue from selling A units to selling B units. So like, for example, the integral from 100 to 200 of R prime of X dx would not give you total revenue from selling 200 items. What it would be the gain in revenue from selling that 101st to 200th unit. Like selling the gain in revenue from selling the second 100 units. It's the change in revenue. So again, a definite integral of a rate of change represents net change. In this case, the rate of change is revenue, so it's the rate of change of revenue. So then the definite integral is the net change in revenue. All right, how are we so far? Any questions so far?
None.
Okay, none from Christopher, he's good. Anyone else? All right, not seeing any. So part B says how much additional revenue is gained if sales increased from 40 to 50 units. Oh, well, we talked about that. The definite integral is the additional revenue gained. So we just want to integrate from 40 to 50. So part B we're just going to do the integral from 40 to 50, and r prime here was cube root or square root? Cube root, okay? And I'm going to do that. That's just like with derivatives, you don't want to do derivatives with radicals. You want to think of them as exponents. So we're going to do that here too. 40 to 50, x to the 1/3 dx. And then we're going to do the opposite of our power rule. Power rule, when we're doing derivatives, we multiply in front and subtract. So now we're going to do that in the opposite order. We're going to add 1, so that'll be 4/3, and then we're going to divide by 4/3 and evaluate that from 40 to 50. And dividing by 4/3 is the same as multiplying by 3/4, and then it will be 50 to the 4/3 minus 40 to the 4/3, and then we use a calculator and whatever that answer is. I have no idea. And that'll be, whatever that is, that'll be in units of $100, because it's 100, the revenue, the rate of change is $100 per unit. And so here you have to multiply by $100, whatever that amount is, you multiply that by $100. Here, this is kind of awkward. The integral is that, so that's the integral. But then when you interpret the meaning, will be this number times $100 gained. All right, and here's where I would look at the room and kind of gauge the looks in everyone's eyes to see if they understand. Chantel, you got to represent. So Christopher, does that answer your question? Or?
Yes.
Okay, all right, good. Anybody else need additional clarification here on number 65? Okay, I really can't overemphasize the value in understanding that a definite integral of a rate of change represents the net change. In fact, we're going to have a question like this at some point, maybe on the quiz today, maybe on the final, maybe both. You're going to get a lot of credit if you even just say, if I ask, oh, what does this mean? And you're kind of lost in the context, and you just say, well, I know it's supposed to represent the total change in something, and you just write total change. Like, that's incomplete, because it should be total change in what, from what to what, right? What is f? It's the total change in whatever that function is, and so you're gonna give meaning there, new words, and then what do a and b represent. But if you even have this solid understanding of, okay, I know definite integrals, when it's a rate of change, they represent total change. That's great, that's really important. Okay, good question, good one to get us started here. Any other 5.3 questions?
Yes, can we go over 11, please?
Okay, these are a little funkier, and these are so abstract. These fundamental theorem of calculus part 1. I struggle with these because, like, the meaning I like to really make sure you understand the meaning behind them, and it's like it's almost impossible on these. These kind of just become a game where you fill in the blanks, and it's just unfortunate. The idea for the fundamental theorem of calculus is you're integrating from a to some x of some f of t. So the function is a function of t. And so you'd integrate from a to x of f of t dt. And then you wonder, like, well, what's the derivative of that? That integral is some area, and the area is a function of x. And so what happens when you take the derivative? That's what the fundamental theorem of calculus is, that first part. And what it turns out is the rate of change of that area is actually just the function value right at x. Kind of like, think about infinitely many rectangles and how fast is the area changing? Well, it's just changing that height at f of x. That's kind of what it's saying. So when you have a form like the fundamental theorem of calculus, all you do is plug the x in for the t. But Sandra's question has more to it. It's not just an x. It's a 2x cubed. So I'm going to give you a hint here. What if I do a little substitution and I let u be equal to 2x cubed? So then I want to try the derivative with respect to x of the integral from 1 to u of the square root of t squared plus 1 dt. Well, if I I'm going to see if I can, it's so hard. I like to physically cover things with my fingers and my hands. And when I cover it with my finger, you can't tell. It just kind of messes with the screen. Whoa, speaking of messing with the screen, where'd everything go? Whoa. So I'm going to try to pretend I'm covering up the dx. Okay. So, oh, I got totally sidetracked. Oh, so if we didn't know it was x, and we were just saying, well, this is a fundamental theorem of calculus, we would just say, well, the theorem says you put the u in for the t. So this would be square root of u squared plus 1. The problem is we're not taking the derivative with respect to u. We're taking the derivative with respect to x. So we need to multiply by something. And there's a derivative rule that is...
Chain rule?
Yeah, you're right. So we need to multiply by the derivative of u with respect to x. So we get the square root of, what was u? 2x cubed squared plus 1 times, and then the derivative of 2x cubed is 6x squared. Now, a lot of the things we do, we can get a good graphical meaning behind it. We can get some explanation for what it represents, like the definite integral. We just talked about it. There's a very clear meaning for the definite integral. For this one, yeah, I got nothing. It's very abstract. And the meaning of it, you're well, then why are we learning it? There's 3 things in the calculus sequence where you kind of need this and it comes up. And there's an important theorem that you're gonna, and this is only for those taking Calc 2 and beyond. There'll be a time where they'll say, hey, remember the fundamental theorem of calculus part 1, where you didn't really know what it was? Well, now you need it. It's not a really good, it's not a really motivating thing to try to understand it. So for now, we're just kind of trying to plant the seed in your brain and oh yeah, you kind of plug in the upper limit. And if that's a function, you do the chain rule. Just trying to understand the mechanics of it. The true meaning behind it will maybe become relevant to you later, but we're just planting the seed now for those that it'll be relevant for. Are we good on that one, Sandra?
Yeah. Thank you.
No, you're very welcome. Okay, any other 5.3 questions? Uh, 71B. 70, that's a big number, Haley. I don't know. Those make me nervous. 71B. All right.
I was just wondering if, because it says, is it even or odd or neither? Is it just asking if the x squared is even or odd or neither?
Yeah, the function. Mm-hmm.
Okay.
Yep. Do you know why that's important or relevant?
No, I do not.
Yeah, let's do a graph of this. Let's do a graph. I think that will help. Oop, shrunk it down too small now. So let's draw a quick graph of this. X squared, we know, is a parabola, and we're kind of not to scale here. Well, the x and y axis aren't the same. I guess that's fine. So I have a dead, what the heck? Oh, I see. I copied something from the previous one. All right, so -4 to 4. And of course, this will be, it's not the same scale, it'll be 16, right? So the first one, we're going to do the integral from 0 to 4. And if we do the integral from 0 to 4, that's easy enough. That is, let's see, x cubed over 3, right? The antiderivative, we're going to add 1 to the exponent, divide by the new exponent, and then from 0 to 4. So that will be 4 cubed over 3 minus 0 cubed over 3, so 64 thirds. So now the question is, this is the real reason what they're asking here, is what would be the integral from -4 to 4? And can you do it without doing the integral again? That's what they're asking. So does anyone have any thoughts? How we could do that without doing the integral again, just with what we have written on the page right now?
We can take the previous one times 2.
Everybody see that? Yeah, that's good, Sandra.
Does it make sense?
Did you say it doesn't make sense to you?
Yeah, because I just say it like that. I'm like, what?
Yeah, so if you look at the picture, this is a symmetric function. And so the red area and the blue area should be the same. So yeah, just double the previous one. Now the point is, you can't do that for every function. What has to be true about the function in order for you to be able to do that?
Has to be greater than 0. It's for it to be positive, because you're saying if it's negative, it's...
Yeah, so I like your point. Let me just quick sidetrack. I don't want to waste too much time, but suppose there was a negative in front of it. Suppose it was y equals -x squared, and we were going from -4 to 4. These would be negative numbers now because they're below the x-axis, but they would be the same negative number. So you could still double it. So my question is about the doubling. When is it okay to double like this?
If the graph is even?
Yeah, and that's why they want you to check that even symmetry. It's only true if you have even symmetry, meaning you can fold it over the y-axis. That's even symmetry. And that's true when f of -x is equal to f of x. So it's not something that you have to do. You can do this integral from -4 to 4 by doing x cubed over 3 and plug in 4 and subtract plugging in -4, and it's fine. It'll totally work. But sometimes you can simplify your work, and we do this a lot. In fact, we were using this a lot in Calc 3. This came up, we're like, wait a minute, there's symmetry here. Let's just double from 0 to 4. And so it's a really useful skill. And then on the other side of it, what if I integrate from -pi to pi of sine of x dx? Pi, -pi, okay?
It's going to be 0.
It is. You don't even need to do any work. Yeah. And how'd you know that, Sandra?
Well, it's like upside down.
Mm-hmm.
Yeah, the first one is like below and the other one is above by the same number. So it's going to cancel each other out.
Yep, exactly. So this is odd symmetry. When this is true, this is odd symmetry. And that means f of -x is the opposite of f of x. Hopefully that looks familiar. We haven't used symmetry a lot this semester, so you might not remember that. I'm sure you've learned it at some point, but hopefully it at least looks familiar. So yeah, so that's useful. It's useful. You could still do this integral. You can do the antiderivative of sine x. That's negative cosine of x. And then from -pi to pi. So that's negative cosine of pi minus cosine of -pi. And let's see, cosine of pi will be -1. There's like, everything is negative here. Cosine of -pi, also -1. and you get 0. That's a lot of negatives, but you get 0. But that was a lot of work. Recognizing what Sandra recognized, wait, this is odd symmetry, this is just 0, way more efficient. So this is, noticing symmetry is like an efficiency thing. It's not required at all. Well, I take that back. There are some integrals that you cannot do because you can't find the antiderivative. But if you recognize the symmetry, you would be able to do. So I take it back. There are some times where it is useful. But in these particular cases, it's not required. And for most of the examples you're looking at, you don't need to notice the symmetry. But if you do notice the symmetry, that's very helpful. So that was a long answer to your question, but I think we clarified, Haley, what that B meant. It's the symmetry of the function inside. Okay, any other questions on that one, on 71? Okay, any other 5.3 questions? I'm going to move to 5.4. We had a question earlier from Christopher about number 15. Let's see here. And then we're going to need some more information here. I'm going to have to flip back over there because there's some more information that's going to be relevant. All right, so first, we have a definite integral, and the properties of integrals say when we have a sum or a difference, I think we mentioned that last time, subtraction is just adding a negative, we can take the integral of each part. So this will be the integral from 1 to 5 of 2f of x dx minus the integral from 1 to 5 of g of x dx plus the integral from 1 to 5 of 3x squared dx. That first one, this is another property of integrals. When you have a constant there, just like with derivatives, the constants can get multiplied. Well, for antiderivatives, the integrals, the 2 can come out in front. So we could write this as 2 times the integral from 1 to 5 of f of x dx. And I'm just going to recopy everything else. Actually, let's go ahead and do that integral at the end. So 3x squared, the antiderivative would be x cubed, and then we'd evaluate it from 1 to 5. And then I think we got to go back to the homework here. We have some information. What do we have? Ooh, look at this. They're being sneaky. We don't have the integrals from 1 to 5, but we have the integral from 1 to 3 and the integral from 3 to 5. Well, that's just mean. Okay, I gotta copy that. I'm not gonna remember all those. So we're gonna do a little side work now. We're gonna do some side work. Oops, sorry. So I'm gonna go over to the side and try to figure out the integral from 1 to 5 of f and g. So the integral from 1 to 5 of f of x dx, another property of integrals says you can do from 1 to 3 and then add from 3 to 5. So that will be 5 plus 2 equals 7. What you're doing here is you have some function, we don't know what it is here, but you're going from 1 to 5, and you're trying to find the area under that. And you could go from 1 to 3, find that area, and then add the area from 3 to 5. So you're just breaking it up. As long as they're all connected, you can add those together. And so similarly, the integral from 1 to 5 of g of x dx is the integral from 1 to 3 of g of x dx plus the integral from 3 to 5 of g of x dx. And that one is -2 plus 1, so that's -1. We're going to then pull those over here. 2 times 7, that one was 7, minus, and then this one was -1. And then here we'll just do 5 cubed minus 1 cubed, just the normal evaluating that definite integral. And so we get 14 plus 1 plus 125 minus 1, and that's 139. Did that clarify for you, Christopher?
Yes.
Okay, good. Any other questions on 15? Okay, any other 5-4 requests?
21.
Oops.
Want to know if I set it up right.
Okay, so what do you mean set it up? What are you thinking? What's
Given the indefinite integral of 1 plus 2 secant times tan secant, so I split it up, and I have indefinite integral of pi over 4, well, negative pi over 4 to pi over 4, 1, plus 2 times the indefinite integral of negative pi over 4 to pi over 4 secant tangent, and I can turn the secant tangent into the antiderivative of secant x.
I think what you mean is, yeah. I know what you mean. So you mean, yeah, so it just becomes secant of x.
Yes.
Right. From negative pi over 4 to pi over 4.
Yes.
Yeah. And then what about the 1?
The 1 turns into an x from negative pi over 4 to pi over 4.
Yeah, everything looks great.
So that becomes 2 pi over 4, correct?
Right, because it would be pi over 4 minus negative pi over 4. Yep. And then we have 2 times secant of pi over 4 minus secant of negative pi over 4.
And secant pi over 4 isn't it just like 2 over square root of 2, right? Because it's the opposite of.
Right, it's the reciprocal. Yep. You could also think of cosine of pi over 4. A lot of times we think of it as square root of 2 over 2, but you can also think of it as 1 over square root of 2. So then the reciprocal is just square root of 2. But 2 over square root of 2 is also square root of 2. If you rationalize it, you'll see. So yeah, so that one's square root of 2. And then secant of negative pi over 4 is the same. It's the same x coordinate on the unit circle for the cosine. So interesting. So we just get pi over 2. Yeah?
Yes.
Okay. The important part here that's new to us is this antiderivative and the fact that Christopher noticed there you can split it up into 2 integrals with the one separate from, oops, I went out of focus here. One is separate from the secant of x tangent of x. So you split it up and then kind of do those separately. And then it's just kind of trick stuff. And, You do have, calculators handy, so you can use some of that technology. Hopefully you don't need it, but if you do, you can use it to check your work. No decimals though. You got to give me an exact answer. So you can't like use your calculator to do because you can do definite integrals on your calculator. But it's not going to give you pi over 2. It's going to give you 1.7 something, whatever pi over 1.5, whatever pi over 2 is. 1.51 something. All right, any other 5.4 requests?
Can you show me the setup for 27?
Yeah, this one is just like with derivatives. You can do the quotient rule if you were doing a derivative, but that's like a really hard way to do the problem. I don't know if you remember with derivatives, we would split it up. We would divide them each by x to the 4th. And so that's what you want to do. Yeah, that's what you want to do here as well. So x squared over x to the 4th minus 12 over x to the 4th. And so then again, just like you did for the previous one, we can break it up into 2 integrals. I'm going to simplify the first one. It would be 1 over x squared, and then minus integral from 1 to 2 of 12 over x to the 4th. And then just like with derivatives, exponents are easier to deal with than fractions like this. So let's write these with negative exponents. X to the negative 2nd dx minus, I'm going to put that 12 out in front. I'm using that other property of integrals, x to the negative 4th dx. And then now you can do the power rule. The antiderivative of x to the a dx is x to the a plus 1 over a plus 1. So you can do that here, even when the exponents are negative, that power rule will still work. The only time it doesn't work is when a is negative 1. That one, you remember, that one's the natural log. But otherwise, you can just do the power rule. So does that agree with what you had, Christopher? Does that look okay?
Yes, thank you.
Mm-hmm. Yeah, you're welcome. Okay, any other questions? $75, all right. And are you asking about, I'm assuming, parts B and C?
Can we go over the whole thing?
The whole thing? All right.
Yes.
Sounds good. Whoa, so big. All right, so area under the curve would be the integral from negative 1 to 2 of x squared plus 3 dx. That's part A. Just finding the area under the graph for the function here. And so antiderivative, that would be x cubed over 3 plus 3x from negative 1 to 2. So I'm doing that power rule, adding 1 to the exponent and dividing by the new exponent. And then if your derivative is 3, that means you started with 3x. Okay, and that's 2 cubed over 3 plus 3 times 2 minus negative 1 cubed over 3 plus 3 times negative 1. And that's 8/3 plus 6 minus negative 1/3 minus 3. And I'm actually, since there's thirds in both places, I'm not going to combine the first two and combine the second two. I'm just going to say, well, this is 8/3 minus negative 1/3. So that's 8/3 plus 1/3 is 9/3. And then you have the 6 plus 3. So it looks like we actually get 12. 3 plus 6 plus 3. I feel like this right now is, I don't know if you've ever helped, like if you have a younger sibling or a cousin or somebody, you're helping them with like, I don't know, adding fractions or something that's like, you know, to them it's like this new concept, they're still learning it. And, you know, for you, it's like, oh, you just need common denominators. They don't really know what that is or what any of that means. And you're kind of helping them through that. So for them, it's a big deal. So right now in Calc 3, I'm doing triple integrals, like 3 of them. And so now when I'm coming back to Calc 1, I feel like I'm worried about going too fast because it seems so simple relatively. So just stop me if I'm going too fast, because I know it's not, it's new to you, and it's a new thing. So hopefully that was okay. So that's part A. Then part B says find the average value. And I think if I remember, your notation in your book is like y with a bar for the average value. That's relatively standard notation. It's not universal. And so for the average value, what you do, think about regular average. You add them all up and then divide by however many there are. In this case, adding them all up is the integral. So you integrate from -1 to 2 of the function. And then you can't divide by how many there are, but you divide by the length of the interval. So you do 1 over 2 minus -1. That's the length of the interval. So what we're going to do is that's 1/3 times our integral, 12. So we get 4. The average value for this function is 4. And I'm going to actually draw that up here and draw 4. And I think that actually seems plausible because it starts at 4, kind of goes below 4 for a little bit, and then goes above 4. So it's plausible. It makes sense to me. They're reasonable that the average value is 4. If I had gotten like 2, that wouldn't make any sense to me because it's below that. It doesn't make any sense. Hold on just a second. All right. So now the question though is interpret the results geometrically. So here's what this average value means. It means if I drew a rectangle under 4, it would give me the exact same area as the integral. And in fact, the area equals the width is 3, the height is 4, and you get 12. So that's part C. How's that, Haley?
Good. I had all the right work. It's just I had the interval from 1 to 2 instead of -1.
So you're like, I'm not getting 12 here. What's happening?
Yeah.
Yeah, okay. All right, good. All right. I think what I want to do now, if you have other questions, if you could hold them until after class or email me. I want to do some examples from 5.5. This is our last section, and we'll do some on Monday as well, but it's a really important one. And so I want to spend more time here. Essentially what these are all examples of kind of casually here. It's the reverse chain rule. It's when you have a function inside another function. And if you look at all of these, some of them are more obvious than others, but like example 1, there's a 2x inside the cosine. For the second example, there's an x cubed plus 1 inside the square root. Example 3 isn't quite as obvious, either as example 4, but look at example 5. There's a 4x inside the secant squared. So there's this like nested function. So this is all about, it's called integration by substitution. And I don't know if you remember when we first did the chain rule, we did it as substitution. Like we did, well, let's let u equal, and then we did a substitution. That's what we're going to do here as well. So for example 1, I'm going to let u, and u is usually like the inside function. So I'm going to let u be 2x. And then I'm going to find the differential du. And so I don't know if you remember this, it's been a while. If y is equal to f of x, we know dy dx, the derivative is f prime of x. But if we want the differential, that's just dy, that's f prime of x dx. So the differential du is 2 dx. If I go up to the integral, I can actually do a little rearranging here and call this the integral of cosine of 2x times, and I'm just going to put the 2 with the dx, 2 dx. And now with my substitution, I can actually rewrite this. And this is the substitution step. Equals, now it becomes cosine of u times du. So that step right there, that's the substitution step. Now I've rewritten the integral in terms of a different variable, u. But I've also made it easier, and that's what should happen. That's the point of this strategy. Because you know the integral of cosine u. What is that? What's the antiderivative? The antiderivative of cosine u.
Sine u.
Sine u. So this would be sine u plus c. And I'm basically done, but I have to put u back in. So this would be sine of 2x plus c. And this is a pretty typical example from integration by substitution, where you have, it's not just a function of x, it's a function of like 4x or 2x or something like that. That's a pretty common one that you'll see on the final for sure. We'll have a couple like that from this section. For those that are going on to Calc 2, pretty much every integral will have this. So you'll get really good at it. You'll have lots of practice. One nice thing about these is you can always check. You can take your derivative of sine of 2x plus c, and the derivative of sine of 2x is cosine of 2x, but then you have to do the chain rule times 2, and then of course the derivative of c is 0, and you can see, oh yeah, that's what I started out with, so I'm good. So it's a nice thing for antiderivatives like this. You can always check. You can always check your work. All right, let me do another one, and then I'm going to pause and we'll see what questions you have. I'm hoping after a couple, maybe seeing 2 of them will help. So you can see the inside part here, there's a square root. I want to look inside of that, that's x cubed plus 3. So I'm going to let u be x cubed, or x cubed plus 1, excuse me. X cubed plus 1. Then du will be the derivative of that, 3x squared dx. And again, if I rearrange this, I have the square root of x cubed plus 1 times 3x squared dx. And so conveniently, this is set up to substitute in for those 2 components there. This becomes the square root of u du. So substitution should lead you to a simpler integral. That's the goal of it, is it makes it from, like, look at that first integral. I don't know how to do that in my head. Integral of 3x squared times the square root of x cubed plus 1. Are you kidding me? But now, after I do this substitution, it looks way more manageable. And that's the goal of this strategy. From here, I would do a power, u to the 1/2. And then we have our power rule, where we add to the exponent u to the 3/2 and divide by 3/2 plus c. And then instead of dividing by 3/2, we can write it as multiplying by 2/3. And then we just plug back in what u is. 2/3 times x cubed plus 1 to the 3/2 plus c. So the problems can get more challenging, but these examples right now, these are not like, okay, these are the ones where we introduce the idea, but all the problems you're going to see are harder. Like this is it. These are substitution problems. We'll see some like this. We'll have probably one like this. We can't have a lot of them on the final because you have the whole semester, so we'll have probably 2. And one of them will be this difficulty level, something like this. Okay. I feel like my internet is slow because at least on my video, I'm like lagging. I don't know if I'm lagging for you too, but anyway. All right, any questions about the first couple?
I have a question about example 2.
Go ahead.
What
Yeah.
happened to 3x squared?
Yeah, the 3x squared was with the dx, and that became du. And then when we integrated, you kind of, after you do the substitution step, once you're at this substitution step, you kind of reset your brain and say, well, how would I do the integral of the square root of u du? Just that. And then the du is just part of the integral, and the du just kind of goes away when you do the integral.
Okay.
And yeah, so it's just because of the substitution that 3x squared dx just becomes du. And then when you integrate as part of the integration process, that is no longer part of the answer.
Oh, okay.
And that will always happen. You know, that du part is just when you do the antiderivative, that just goes away.
And that will always happen, you said?
Yep, some version of that will always happen.
Okay.
We'll see in some later examples here. It's not always, sometimes you have to tweak it a little bit, but. Any other questions on the first couple? All right, let's do it. 3 and 4 are similar, where it's not really an inside function. It's like 2 functions next to each other. And you're like, well, I mean, on 3, you could just say, you know what? I'm good at algebra. I'm just going to multiply these out because it's just a polynomial. Fair enough. You can do that. That's fine. But one option you can see here, I don't know if you notice the relationship. Does anybody notice there? If you get good at this, the more of these you do, where the first factor is actually the derivative of the second factor. So you can let u be equal to x cubed plus x. Hold on, I'm getting interrupted again. Just really needed to tell me that he's going to go read on the hammock. Thanks, buddy. It's good to know. Okay. So when we find du here, we take the derivative, 3x squared plus 1, and then dx. And now you might see, like, you might have some misgivings, like these always seem to match perfectly. What happens if they don't match perfectly? Sometimes you have to adjust it. Well, these are the first examples. The first examples, they match perfectly. They won't always match perfectly. But I'm going to rearrange this like I've been doing. That 6, you notice, is just kind of extra. I'm going to put the 6 out in front. And then I have x cubed plus x times 3x squared plus 1 dx. And that's my du. Then the first one is my u. So now this becomes 6 times the integral of u du. And you see, much simpler integral. This integral is a power rule. Add 1 to the exponent, divide by the new exponent, plus c. And just to Sandra's point, just like the previous one, the du is just part of the integration process. Once we integrate, it's gone. And then we just simplify. 6 over 2 is 3. U is x cubed plus x, so that's squared, plus c. So sometimes you just have two functions that are right next to each other, but one function is the derivative of the other function. We can see that with example 4. Now, yeah, either one will actually work, but can you think of which function would make a better u?
The sine of x.
I agree. Why would you choose that, Chantal?
Oops. When you do the antiderivative, it's going to go back to sine of x. It'll be the same.
Not quite. Not quite. Well, hold that thought. But I do think sine of x is a good choice for u. Does anyone know why I think that?
Because 2 sine x cosine x equals sine 2x.
Oh, you could do that. That's fancy. That's
Okay.
not what I had in mind. Haley, are you going to answer?
Because the derivative of sine of x is just cosine of x, and then it would be cosine of x of dx. And then if you had u of cosine of x, then you would have du equals negative of sine of x dx. So that would just be like more additional work that you would have to do if you did the u.
Everybody catch all that? That was exactly what I was thinking. It's not that you can't do u equals cosine of x, but you have additional work. Here, if we let u be sine of x, well then cosine of x dx is just du. And so this just becomes the integral of 4 u du. But I will say, I do like Sandra's idea that you could do it that way too. You'd actually get a different trigonometric expression, but an equivalent one. You know, like think of a trig identity where they're equivalent. So you could do that. That would work to use that trig identity, Sandra. But that's super, that's fancy. That's the official mathematical term for that. It's fancy. So u substitution here, we let u be sine x, du is cosine of x dx. So then we just have 4u du. We use our power rule, u squared over 2, and that's 2u squared plus c. And then we substitute back in u is sine of x. Usually we would write that 2 sine squared of x plus c. All right, any other questions on those two? All right, by now, if we were in class, I would stop talking. And I would say, okay, now it's time for you to try a bunch. And like we would do one of those like walk around and we take 15 minutes. Those days are gone. I miss those days. So I'm going to try to do a couple more here. Let me try to do some that are different. So I think 5 looks pretty similar. Let's do 6. We haven't done one like this. It looks the same as one we did earlier, but you'll see there's a very subtle difference. We have a 4x inside the cosine, so I'm going to let u be equal to 4x. And then du will be 4 dx. And I have a little problem on this one. It's a small problem, but there is a problem. How about somebody who hasn't answered yet today? Does anyone know what the problem is? What's different about this one that hasn't happened yet?
There's the extra 4 by the dx. So you should divide by 4
Yeah,
to get
you'll
rid
see.
of it.
Yep, you'll see here, up here, all we have is a dx. All the previous ones, we had du. We do not have du this time. So all we have is dx. Now, there are different ways to handle this. I'm pretty sure that my method is the same as Dr. Sugar's. I should have watched the videos. I'm sorry, I did not. But the way we're going to do this is we're going to divide both sides by 4 to solve for what we actually have, because all we have is dx. So that would give us 1/4 du equals dx. Now when I do my substitution, I'll have cosine of u, but then instead of just du, dx is actually 1/4 du. And this is very common. Often the constant part of it won't exactly match. And so this frequently happens. You get 1/4. Now I'm going to put that out in front. We have that property of integrals, the antiderivatives, where we can put it out in front if it's multiplied. And the antiderivative of cosine is sine plus c. And then we just plug back in what u is equal to 1/4 sine of 4x plus c. Excuse me. So this is very common where you have to adjust for this constant like this. Any questions on that first one? All right, let's do one more. It might be all we have time for. You can see there's an x squared plus 1 inside. So that kind of leads us to believe we should do u equals x squared plus 1. Let's find what du is. Du is 2x dx. But again, I don't have a 2x dx. If I rewrite the original integral, I have x squared plus 1 to the 5th times x dx. That's all I have. All I have is x dx. So it's no big deal. Just like Haley said for the previous one, we'll just divide by that constant. We'll divide both sides by 2. So 1/2 du will be x dx. And now this becomes u to the 5th times 1/2 du. And that's 1/2 integral of u to the 5th du. Once you do the substitution, the integrals should be simpler, and this one is. And this is just power rule, u to the 6th divided by 6 plus c. Or 1/12 times x squared plus 1 to the 6th plus c. And like I said, you can always check the derivative with respect to x of 1/12 x squared plus 1 to the 6th will be 1/12 times, and then we do the power rule, 6 times x squared plus 1 to the 5th. But then we need the chain rule. The derivative of the inside is 2x. And then derivative of plus c is 0. And you get 12, simplifies with the 12, you're left with x times x squared plus 1 to the 5th. And it checks. So questions on that one? All right, we have many more examples to do. We are nearing the end of our time. I'd like to do one of these definite integrals with you, so you at least have one as a reference, but there's many more. The rest of them are definite integrals here. So let's see, I guess we only have 2 more after this, but we'll do more examples on Monday. We'll do more homework questions, we'll go over the quiz, but let's do one here. And you'll notice this one is a definite integral. So this is going to be a little bit different. You have 2 options here, and I'm going to do this way because we only have time to go through this once. So I'm going to show you the way that I usually do these. So I'm going to do a substitution again. U is 2x. We've seen this before. Du will be 2 dx. All we have is a dx, so we'll divide by 2, and we get 1/2 du equals dx. Now what's different about this is I'm going to write something here that is actually mathematically incorrect. I'm going to do the substitution and then 0 to pi over 2. So there's something about what I've written there, and if you want to just wait to write it, so you don't have to erase, that's fine. Something about what I've written there that's actually incorrect. This equality sign is actually not true. It's not actually equal, but it's very subtle. And do you know what the error is, why it's not actually equal?
The integral from 0 to pi over 2, that's wrong because that's for x, and we have u's.
See, these are x values. That's exactly it, Haley. These are x values. X goes from 0 to pi over 2. So what we need to do is, I'm going to erase the limits. We need to figure out what the u bounds would be. And what I do for that is, well, u is just double x. So I kind of think of it like a function. Well, what's u at 0? 2 times 0. Well, double 0 is still 0. And then u at pi over 2 is 2 times pi over 2. Oh yeah, double pi over 2 would be pi. And so now that equality statement is true. Here's what's interesting about, well, we're going to finish this up. I'm going to go a little bit late. I feel like I'm doing this every day. Always going a little bit late. So it's 10:35. You are free to go. Don't feel like you need to stay. You can always pick up and start watching the video replay, right? At, what would that be? Because we're like an hour, 5 minutes. So you can start watching the video at like hour 5 if you want, and pick it up from here. So let's keep going. We're going to pull a 1/2 out in front, 0 to pi sine u du. Ooh, we haven't, I don't know if we've done the antiderivative of sine today. I think we did. I know Haley, somebody talked about it. Who remembers the antiderivative of sine?
The antiderivative of sine is negative cosine u? Or
Yep. No, it's you. It's you. You're right.
Oh, you.
Yep. Trust yourself there because it's the variables here. Yep, you got it. Exactly. All right. So I'm going to write this as negative 1/2 times cosine of pi. So I put the negative with the 1/2. Negative 1/2 times cosine of pi minus cosine of 0. That's negative 1/2. Cosine of pi is negative 1. Cosine of 0 is 1. So we get negative 1/2 times negative 2. So we get 1. Interesting. Okay. So I want to finish today with a Desmos graph. 2 Desmos graphs, actually. So what I want to do is I want to graph y equals sine of 2x. And I only want to look at the area underneath that. We're going to call this, we're going to call this y1. We're going to graph 0 less than or equal to y less than or equal to y1. Between, x was between 0 and pi over 2. Oop. Okay, so that's the integral we were looking for, was that area right there. That was the integral, that was of sine of 2x from 0 to pi over 2, okay? What we did instead was we looked at the graph y2 equals sine of u. And I'm gonna shade 0 less than or equal to y less than or equal to y2 from, oh no, it was 1/2 of that. Yeah, from 0 less than or equal to u less than or equal to pi. Oh, I think I need to make these x's. Desmos is getting confused with the u's. Okay. So the purple area is the second that we computed. So check that out. We kind of changed the graph from sine of 2x from 0 to pi to the sine of 1/2 sine of x. Sorry, the first one was from 0 to pi over 2. Then we changed it to 1/2 sine of x from 0 to pi, but that blue area and the purple area are the same. So we like changed the integral to an easier one, but the areas underneath the curve are the same. They're the same area. So that's the point of this substitution, is you make it into a different function that the area under it is the same as your original one. Okay, if you have not watched all of the 5 videos, and there are many of them, try to do that over the weekend if you have some time, but you're also going to be studying and kind of looking at old exams for the final. So I know you have a lot to work on. I'm going to put a note to myself to post blank old exams and link to the YouTube video solutions as well to those. So in addition to all the other stuff you have going on, you can also start looking at some old examples. The final, if you're preparing for it, will be like a mixture of things from the different sections, but we'll try to do like at least one problem from every section in chapter 5. So we'll try to make sure that everything from chapter 5 is on the final, at least one example from each section. The other ones, it'll just be little snippets from them. If you have questions about stuff, about like what's going to be on the final over the weekend, the Discord chat would be a great thing, because then everybody else could see my response, like, yes, prepare for that. No, don't prepare for that, kind of things like that. So, and we'll talk more about that on Monday and Tuesday, but if you're thinking of it this weekend, post it while you're thinking of it. That would be a really good idea. Yeah, the quiz should be posted, should be live now. It should be on D2L. Let me just hit refresh here. Whoa.
It's due tomorrow.
Quizzes are due Thursdays, so it is due tonight.
Right? Okay.
Yep. If you have to work or something, and you don't have time for today, I know some people's work schedule changed, just shoot me an email and let me know.
All right.
But yeah, it should be up there now. Let me double check here. I did program it, but sometimes I forget. And yeah, quiz 11 is attached. So, all right. Any other questions? All right, I am going to stop the recording.